Our next presenter is Goksel Dedeoglu from Texas Instruments. Goksel is a manager of the embedded vision team at Texas Instruments, and where he and his team design embedded software for real-world applications, tackling challenges in automotive safety, video security, and gesture recognition. Goksel earned his PhD in robotics from CMU, where he specialized in computer vision, and also graduated from USC and the Istanbul Technical University. Please welcome Goksel.
Thank you, Jeff. And thank you all for being here this afternoon. I'll be talking about the application of moving object segmentation for security surveillance type of applications. And this is work I have prepared with my colleague Darnell Moore at the Systems and Applications R&D Center at TI. And we do have a nice group of vision experts, and we do all kinds of fun vision projects on embedded processors. And this is one of the examples of the kinds of things we do. So, as you have seen in many examples, cameras are everywhere now. So they are in our public spaces, offices, retail spaces, if not at home already, watching out for intruders or not, and for whatnot for us. So the one thing that's very clear already is that there are more cameras than people can watch, can sort of supervise and sort of analyze live. So there's an obvious need for automatic analysis and information extraction out of these video streams. And this has been actually the long-standing goal of computer vision for many decades at this point. Well, if you have too much data to analyze, and if you just don't know how to sort of solve this problem with humans, let's just come up with algorithms, with solutions, and let's program computers to attack the problem. And so that whenever there's something interesting going on, and only when there is events happening that we care about, we get notified about them. In the video security world, the applications of computer vision are known as video analytics. It's really just a terminology thing. In sort of inspection kind of context, computer vision tends to be called the machine vision. If it is embedded, we call it embedded vision. And you'll hear me say analytics quite a bit. That's because of the video security context and nothing else. So imagine you're interested in doing this, and you might be in some R&D lab, you might be prototyping something. Typically, you tend to do these things on a PC in a desktop environment. Algorithm development takes a lot of iterative trials. We tweak algorithms, we try out totally new ideas, and we throw away what doesn't work, and we like to keep what works. And that's all good and fine, but what needs to happen is that these algorithms need to transition from that PC environment onto an actual product form factor and product environment at some point in time. What do they look like? Well, for video analytics, they typically tend to come in these two forms. One is a server-based approach, where you might be feeding your existing camera infrastructure, typically analog cameras, into a DVR, digital video recorder, and you might want to do video analysis in that DVR box. Or you could be actually leveraging one of the newer generation cameras, which it might be already a digital camera, a smart camera, and you might be deploying a video analytics solution in the camera itself on the edge. But no matter which way you go, you are going to want to be able to deploy a power efficient, yet still sort of high compute power compute platform out there, so that you can analyze these videos at the server or on the edge and consume them as the user and get your alerts and information about the events, let's say through the web, on a PC, or on your mobile phone. So these form factors are going to determine a lot of things about how one can go about embedded vision and what the sort of the optimal platform might look like. There's going to be many challenges. Let me start at the application level. Number one, let's stick to the video security use case. You are going to want to detect events of interest in real time. So you cannot afford to wait, do some sort of batch processing necessarily overnight. So this needs to be a real-time algorithm running on an embedded device. And you are going to typically have a very low tolerance for false alarms because you won't have a chance to go back and clean up your results to do some smoothing or some cleanup. And if you don't provide that, the end consumer is not going to like it, and at some point they might just turn off the feature. They might say, video analytics, isn't quite working for me. So the expectations are really high. From an algorithm point of view, though, if you are the developer, you know that this whole problem is not anywhere to being solved, really. There's going to be, imagine you are trying to deploy a smart camera. You don't really know where exactly that camera is going to be mounted. There's going to be scene factors that are not going to be under control, illumination. People are going to turn on and off lights. There's going to be all kinds of effects indoors and outdoors. It's going to rain. The camera that you have mounted on top of a pole is going to keep shaking. And you'll want your solution to still work, though, with minimal amount of user intervention. So nobody can babysit a vision algorithm out there. It's expected to be doing the right thing under all these varying conditions. And most relevant to the fact that we are doing this in an embedded fashion is that the compute platform is going to need to support all these functions, all this solution in a low power, low cost, and high performance fashion, because you're going to potentially need to analyze a lot of pixels at high frame rate. And because these solutions are still developing, it's such a nascent field that the algorithms themselves are changing in a dynamic fashion. You'll probably want a programmable platform to be able to go back to your solution and do iterations on it. And that device is going to need to interface with the world as well. So you'll probably want internet connectivity and things like that. And as I said before, high resolution, high frame rate is definitely the driving theme in many of the camera applications. So these are the challenges, and I'll try to then talk about an application to exemplify what the components might look like. So let's take the moving object segmentation task. Imagine you have a sort of a train station. 5. Okay. So and you're interested in extracting information about moving objects, such as a person crossing the railroad or cars passing by in a parking lot. You'll want to typically analyze the images so that you get some information about the moving parts in the scene, the parts that are changing. And I'm going to give more details about this moving object segmentation part. That's not necessarily do sophisticated processing, such as classifying whether it's a car or truck or inferring things about it. It's just going to draw blobs and identify the pieces that are moving. One way to approach this is to learn a background model and to compare your current frame to the background model you have learned. And we have found out that this tends to be one of the key bottlenecks from a computational point of view in embedded applications. This will be one way of going about it. Real quick, what are these components doing? So at the bottom, you have a background model. You can have different flavors of it. It can be a single Gaussian, mixture of Gaussians. You'll be comparing it against the current observation in the background subtraction step. And typically, you'll want to do some sort of morphological processing to clean up the foreground mask that you have just computed. And something like a connected components analysis to then infer high-level object information, such as, okay, this is one person moving, maybe one blob, and this is a different blob, and there are two different things in the scene. So in the interest of time, I'll just invite you to come see our demo. We have implemented this application using one of our DSP-optimized libraries. And as you can see in the live demo, we are able to get, using the library, about a 10x speed up when we go from just natural C code to a DSP optimized code that is getting full entitlement out of the DSP. Again, very briefly, these are the benchmarks you can come see. The particular demo is going to run at QVGA 10 frames per second. So it takes about 9 megahertz. And it is possible to do more, to do higher frame rates and more resolution. Again, more details can be found later. One key message I want to convey here is that an embedded algorithm can be different from a PC-based algorithm in that it needs to have the right hooks and the right parameters to match the available accelerators on an embedded chip. So one of them is definitely the fact that there's going to be a direct memory access engine, a DMA engine, that will help you move your data efficiently in and out of your external memory onto on-chip memory. So you want your library to support that. And typically these operations in computer vision, these low-level pixel-intensive operations are fixed point operations. So you want to leverage that fact as much as possible. And as I said, moving object segmentation is very relevant to security. And when you take a step back and look at our vision library, you see that a large portion of it is dedicated to background modeling, background subtraction, and the types of functions that I have talked about before. So we have good support for that, plus many other things that are ready to be used for all kinds of applications. And again, so Texas Instruments is a silicon provider, and so that's why I tended to focus on the compute platform end of things. The real challenge is really our customers to come up with the algorithms, with the solutions, with differentiating solutions while meeting these challenges. And I hope that the moving object segmentation demo is a good illustration of this capability. Thank you very much.
Thank you, Goksel, and I would encourage everybody to go see TI's demo and to pick Goksel's brain. This guy knows an incredible amount about both the theory and the practice of embedded vision.